Hello everyone, Assalamualaikum and good morning. Sound check please. Okay, thank you. Alright, before we start, dah ada semua ke? Tak apa, nanti kita discuss something that related to the test 2 at the end of our lectures today. Alright, before that, I think it's better for me to start right away our meeting today with Ummul Kitab, Suratul Al-Fatihah, and to those yang bukan beragama Islam boleh mengikut cara agama masing-masing. Alright, so this is will be the last topic for us for our course, which is on the heat transfer. So another topics on the heat transfer, but in this case, instead of we are to obtain the temperature distribution across across the plates. But in this case, we still would like to determine the temperature distribution, but along the fin itself. So kita tengok in detail. Alright, so our topics today, which is on the heat loss in tin fin. So the purpose of the tin fin itself, one of the purpose is to enhance the heat transfer from the system that generating the heat itself to the surrounding. So the fin basically is an extended surface. So we have a surface that may have high temperature. So we extend that surface we extend that surface to the structures. Then it has been proven that this extended surface, or what we call it as a fin, have a good what we call it is a kind of a efficient kind of surfaces that is releasing the temperature to the surrounding. So kalau kita tengok dekat sini, you may found this fin in many application, engineering application. For example dekat enjin, kita punya motosikal biasanya dekat enjin kereta tak nampak. Enjin motosikal biasanya kita akan selalu nampak lah benda ni. Kalau motosikal yang kecil tu pun biasanya tak nampak juga, mungkin yang apa ni, yang ada yang high horsepower kan, big horsepower tu you may see this. And then alright, so the purpose is still the same. We have the internal heat generation in this in the engine. Ni dekat pistons, dia punya piston ni dekat dalam ni. So there is a high temperature because due to the combustion. So kalau temperature too high, biasanya performance satu sistem tu mungkin dia akan drop. So somehow rather the engineer have to control what is the allowable temperature. So kita pun tak nak temperature dekat surface kita punya sistem tu too high. So kalau nak buat maintenance ke apa, you have to wait for a bit longer of time lah untuk dia cool down ke apa kan. And then in term of the material wise, you have to use material maybe a bit expensive lah sebab temperature tinggi. So kita tak nak certain temperature yang kita pakai untuk our system tu dia akan ada defect disebabkan oleh temperature effects. So untuk haiwan pun there is a fin dekat ikan sebagai contoh, sangat jelas ikan. Untuk ikan bukan saja untuk dia apa ni maneuver, untuk dia bergerak, tapi mungkin daripada sini dia ada the similar effects lah, which is untuk cooling the body ke kan, ataupun mungkin untuk heat the body pun juga kan. Daripada surrounding high temperature area tu. So itu tak sure lah. Saya pun tak baca, tak explore much on the how what is the purpose of fin untuk ikan, other than untuk dia maneuver. Tapi fin also available untuk haiwan. Actually kita punya badan pun sama juga sebenarnya, our hand. Actually kita punya central body kita ni dekat bahagian yang apa ni, generating more heat, which is kita punya jantung kan, dia pumping paru-paru apa semua tu. And then that is a central. So kalau apa ni, kita punya kaki sebagai contoh, tangan, which is like a extended surface from our central body ni kan. So kalau demam, kalau kamu duduk berengkok, duduk rapat-rapat, so dia lambatlah sejuk badan. So expandkan everything. Hopefully dia punya apa tu, heat from our body can release quickly. That means more surface area contact dengan apa ni, dengan ambient tu. So more temperature can be released. So that's something lah. Okay, other than that, ini untuk cooling IC dan juga processors untuk komputer. Sebagai contoh, dalam komputer, you open up your computer, processor is heat generation punya ni component. So lagi banyak kerja kamu gunakan dengan kamu punya komputer, let's say kamu buat modeling something, buat heavy calculation, so lagi banyak kerja dilakukan oleh processor, so lagi panaslah dia. Zaman saya mula-mula around year late 90s lah, late 90s, tahun 98, 99, 2000 dulu. There is a AMD processor. Intel dah ada. So dia punya rival dia masa tu adalah AMD. AMD masa tu orang cakap dia punya panas dia lain macam kalau letak telur atas dia boleh masak telur. So memang panas. And then masa tu there is no fan on top of processors. Dia just processor, then that's it. So sekarang ni dia ada processor, lepas tu atas processor dia ada fins macam gini, and then di atas fin then dia letak lagi dengan fan untuk convection purposes, untuk further increasekan lagi kan apa tu heat dissipation. So untuk cooling the engines, so sama juga. So cooling fluid akan circulate dalam ni, dan dia akan lalu ikut celah-celah enjin ke apa semua, then di hot cooling liquid akan melalui surface ni, dan dia akan releasekan heat tu, dia akan trap dekat sini lah, dekat among the fins. So that's why depan fin kau tengok, kalau kamu buka kereta, bonet kereta tu ada a layer of, dia panggil apa radiator ke apa, saya lupa nama dia. which is something like this, and then you have a fan. Dia ada fan kipas dekat depan tu, so to induce further release ataupun enhance the release of the heat. So that's in general application lah. And then if you go out to the real world, nanti you may see different kind of cooling system lah, yang mana juga menggunakan konsep thin fin. Alright, actually this topic, we still actually looking for heat transfer, heat dissipations across the component, which is in this case our component is the fin itself. Kalau sebelum ni, in the previous topic, what we are doing, which is likely kita buat yang sebelah sini tau. So sebelah sini ni mungkin dia ada a thick plate kan. So something macam gitu dah. So so kita nak tengok sebelum ni the pressure distributed across this plates. Tapi in this case, it's still roughly very similar. Okay, beza dia kalau sebelum ni kita ada plates, then kita ada known boundary condition, specified temperature, and then we may have what we call it convection. Convection in that side, right? So kita boleh ada convection in this side as well. So actually the concept is very similar, cuma in this figure dekat sini, so instead of kita cari temperature distribution in this approach, macam kita rotatekan benda ni 90 degree. So kita ada structure kita which is now is a thin structure only, because fin usually very thin, 1 or 2 millimeter, depend on the application jugalah. Depend on the application. So the convection, as you can see here, convections will occur on both sides. So dia still akan berlaku convection on both sides. And then we know the specific temperature here. So we know T on the kita panggil base. So this is our what we call it main body kan, main body. Which is kita nak releasekan temperature ni, heat ni from the main body. So that mean we know the temperature on the surface of the body tu. Kamu boleh ambil thermometer letak kat situ, then you know what is the surface temperature of the main body. So this is actually represented by temperature of the base ataupun from the surface of the kita punya body. And then usually in this problem we will assume that we will insulate this part. Actually dia punya thickness pun very small, very small very small contributions toward the heat dissipation. So and then what we are trying to do is to obtain the temperature distribution along this fin. Along the fin. So we're still working in 1D. So most of the time, we will involve these three kind of the body condition as well. Kita mungkin ada insulation, insulator included, and then we have specified temperature at the base, and then we will have the convection process on the both side of our fin surfaces. So fin dia ada banyak jenis in term of their geometric shape, geometrical shape. Ada rectangular shapes, ada cylindrical shapes, circular cylindrical shape lah. And then ada yang jenis square tapered, circular tapered. So all of these actually have different performance depend on what you want to do. Then you can choose which type of fin to be used in your problem. Tapi kena buat analisis dulu lah. How much you want to have the heat dissipated from your systems. So the governing equation, we still use the same. So I'm not going to explain further detail. So in terms of the final element modeling, we are still using the same as well. In terms of the temperature functions, we are still using the same. And then in terms of the element connectivity, we are still using the same as the plane heat dissipation, heat convection through the plane wall, which is kita punya previous topics. So in terms of the theory, all of them, which is the same. Okay, when cuma dalam this topic, dalam topik yang sebelum ni kita separatekan. Satunya kalau problem tu ada specified temperature, specified flux. Lepas tu kita ada kita asingkan in terms of when we dealing dengan dia punya boundary condition tu, kita asingkan satu-satu kan. Tapi in this case, it's like we lump it together. So that's why kalau kita tengok kat sini, we have new terms which is known as heat element heat transfer matrix. So saya baca dulu dan saya cuba explain lah kat sini. So it mentioned there, in thin film, heat dissipated primarily by convection. So ini dia punya ni. How the heat dissipated through the thin film, which is mainly through the convection process. So kalau tak ada convection, actually kurang berkesan juga thin film tu. So the effect of conduction through the thin film is represented by the conductivity matrix K. So in terms of the conductivity, so kita dah ada dekat sini. Information dia ada dekat sini. Which is the information of the conductivity coefficient from each material is included in this conductivity matrix. But the effects from the convections is included in this heat transfer matrix. So kalau ingat sebelum ni kan, when we have a problem with a convection, so we have to modify, let's say convection berlaku pada nodes number 1. Berlaku dekat sini kan. So we have to modify K plus H and then R plus HT. Okay, R plus plus by HT, yang lain-lain 000. So yang ni pun sama, so yang lain-lain kita ada K lah, yang lain-lain. So in this case, kita pun ada something similar juga sebenarnya. Tapi the way we write the matrix system of linear equation ni to include the H matrix separately from the K. So nanti kita tengok itu. So the effect of heat transfer matrix is given by this element heat transfer matrix, which is the information from the convection process, which is the heat transfer coefficients. H is included here. The length of element, kalau element of equal spacing. So kena tengoklah elemen 1 berapa dia punya elemen dia. Elemen 2 berapa dia punya size dia. And then sekiranya elemen tu tak equal spacing, then you have to consider lah delta X of each element ataupun delta X dalam kes ni adalah L untuk setiap elemen tu. So the thickness is also considered, even though the thickness of fin ni, which is very very thin, um, but we have to consider to accurately represent these convection effects. Ada soalan setakat ni? So kita accept saja untuk setakat ni all the theories. So we skip exercise. So for the element heat rate vector, which is our R metric. Untuk thin, the element heat rate vector is different to the heat transfer through the plane wall, which is R untuk plane wall is actually calculated based on the internal heat generation kan. Kalau tak ada heat generated in the system, then R will be equal to 0 for every nodal point. But for the thin film, the element heat rate vector is actually contributed from the convection process itself. So ini yang membezakan dia lah. So untuk element heat rate vector, so biasanya kalau fin, kalau kita tengok tadi, if we look at this, kita pergi patah balik kepada figure yang atas tu. Okay. So if you, ataupun yang ni pun okay, yang fan tu okay. So let's say kita letak kipas dekat sini, then this kipas ni dia akan actually instead of dia blow tu, dia actually dia akan sedut udara tu. Dia akan sedut, so the flow will go from this side and then blow upward lah. So that dia release dia pulling cooling air ke sini, ke all the fin, then release all the hot air to the outside of the casing. Kalau kita imagine kita punya apa ni, CPU kan, CPU computer. So apa yang saya nak highlight dekat sini berkenaan dengan heat rate vector tadi, untuk fin, for any fin yang kita ada an array of fin, mungkin ada 30-40 fin dekat sini kan. All of them actually are exposed to the same H and T kan. So kalau let's say saya ambil satu fin, kalau saya ambil satu fin saja, so dia punya convection dia H dengan T usually the same lah, on the both sides. So dia tak akan jadilah apa ni, H yang berbeza kan. Dia sebenarnya mungkin ada beza disebabkan oleh bentuk kipas kan. Sini mungkin exposure dia kepada udara tu, especially di spot lah sebagai contoh. Maybe will receive lesser air lah yang disedut daripada kipas ni sebab small portion je dekat sini. Yang ni will have a greater air flow kan. Tapi in our course, we will make this kind of assumption. Both surfaces will experience the same convection process. Alright. So now we are here. So in thin film, the heat rate vector is contributed also by the heat loss by this convection from the fin. So using Galerkin approach, so kita ada potential energy approach, kita ada Galerkin approach. So untuk heat rate vector, so as we have in this slide. So we are using this Galerkin approach to derive this element heat rate vector, and the element heat rate vector is given by equation H6, which is our element heat rate vector is requires the convections, what we call it, terms, which is H and T. Also the length of each element that we consider, and also the thickness of the fin itself. So again, all the equation will be provided, so you do not need to worry. Kalau pergi kerja pun, kalau boleh hafal, lagi baguslah. Tapi biasanya every time we do the job dekat luar sana tu, we have to always open up the manual, reference book, kan? So we don't expect you to ni lah, to remember everything. Saya kadang nak ingat nama student 30-40 orang pun dah tak ingat lah. If you would like to remember all these equation, lagi susah kan? Alright, now just now what do we have just now? We have the R vector, then we have H vector, and then these two informations is to be included in our system of linear equation. Our original system of linear equation, which is in the form of kt equal to r. So I use capital R here to represent the similar R, but this is the after we assemble to make a complete system, kan? So yang ni small letters yang kita pakai ni, which is to refer to the local element by element. Alright, kalau kita tengok dekat sini, we include the effect of the convection itu straight away in our system of a linear equation, instead of kita solve dia in apa ni differently, part by part macam sebelum ni. Kalau kita tengok, kalau saya boleh recall semula lah yang sebelum ni, let's say if we have a convection occur in this surface of our wall, then the convection effect is only applied to the last node, kan? To the last node. Kita tak perlu pun apply kepada this node, this and that node. So kita just ubah the last equation kita. Tapi in this case, okay, in this case, all the nodes are experiencing the convections. So sekarang ni kita punya element which is in that direction, then convections process to occur all over the surface. So that's why the effect of convection ni is directly applied to the R. Sebelum ni R based on internal generation. Kalau tak ada internal generation, heat generation, then R will be equal to 0, kan? Tapi dekat sini kita tak ada internal heat generation. Memang tak ada. So R, kalau kita nak imagine similar to the plane wall pun boleh. Tapi we have to modify. Kita kena tambah lagi dengan HT all over the elements tu. Tapi untuk memudahkan, to simplify the process, in this example we add the effects of the convections straight away in the R, and to include it in the H matrix, in the H vectors. Sorry, in the H matrix. So that kita punya system of linear equation, sebab convection berlaku pada semua, so we have to modify all K value. So everything ni kena tambah dengan H. So that's why we have the matrix, our matrix here. For all element, we have to add K by H. And then we have the unknown T, and we have R as well, which is elements apa ni apa nama tadi elements heat transfer matrix, yes. So untuk these problems heat transfer, the equations as shown here is embed with the convections effects straight away. Tapi kita ada satu condition kan, which is kita tahu on the surface that is attached to the main component, kita tahu the temperature dia kat sini. So itu nanti kita tengok dalam how we will deal these field problems in term of their boundary condition. Ada soalan setakat sini? So the appearance of the equations looks slightly different, tapi the concept actually still lebih kurang sama dengan plane wall tadi tu. So kalau tak nak keliru, jangan pakai yang plane wall equation dekat sini lah. So kat sini pakai yang this equation straight away. Alright, now kalau tak ada soalan, I think we move to the thermal boundary condition. So in term of thermal boundary conditions, seperti saya bagi tahu tadi, the fin usually will be attached to the heat source lah. Benda yang panas tu dia akan attach kat situ supaya heat will be release from the main body will be enhanced lah in term of dia punya heat release by adding this fin. So in that case, we know at least at one end of the fin, we know the temperature, which is given by T base or T1 or T note in this slides. And then often on the other end of the fin, we impose this specific H flux, which is equal to 0 on the other hand. So sebab dia, which is very thin punya surface, so the heat release from this surface pun which is very minimal lah. So in this case, kalau kita nak tak letak boundary condition, kita tak boleh nak solve. So what we can do, we assume there will be no heat release from the surface by giving this kind of boundary condition, which is heat flux equal to 0 on the right hand side of the surface. Kalau kamu buka komputer tu boleh tengok lah fin dia berapa milimeter dia boleh tebal kan. Saya silap tak sampai pun 1 milimeter, which is very thin. And then macam mana kamu nak measure kalau dah terlalu ni kan, terlalu nipis je. Kalau tebal mungkin boleh kira sikit. So to avoid the difficulties in numerical analysis especially, which is we need to have the initial value dengan boundary values. So kita punya problem ni dia macam fall into the initial and boundary value problem kan. So we need to have this boundary value dengan initial value to close the equation, So when you have this boundary condition applied to the system of linear equation, then we implement the similar process by eliminating the eliminating the row and columns to our system of linear equation, and also the treatments that is required for specific heat flux. So, okay, dia ada example kat bawah ni. Saya rasa better kita tengok, kita settlekan the theoretical part, because this topic is very straightforward lah actually. So, in terms of heat dissipated from the elements, so kalau kita tengok kan in real lah, this is from the finite element analysis. So as you can see, we have an array of fin. Ni, kau boleh nampak ni 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dan seterusnya lah. And then we this is the base. Dekat bawah ni adalah dia punya base. So we have a hotter temperature dekat bawah ni. So and then this is the surrounding. Surrounding we have certain temperature lah dekat sini. Let's say we take T ambience. So the temperature from, let's say kalau kita consider this element, the temperature, if we look at the temperature only, temperature on the right hand side dengan left hand side of this element tak sama kan. Okay, yang dekat sini dengan sini mungkin sama. Sini dengan sini pun mungkin sama. So actually, it's not necessarily to have the same temperature lah at the both side of the fins. Lagi dekat susunan dia, lagi hampir sama dia punya temperature di antara the surrounding the the fin lah, the middle fin, except yang dekat tepi sekali ni. Kalau gap dia lagi besar, so satu kat sini and then the next fin dekat sini, so mungkin temperature tu dia punya gradient dia lagi tinggi kan, so mungkin tak sama. So in reality dia macam gitulah, tapi in our course we have to impose some assumption by assuming convection berlaku sama rata kan. So now let's look at this heat dissipated from an element. It says that the heat dissipated H from a single element can be estimated using the Newton law of cooling given by equation 8a. So the heat dissipated H is actually equal to the heat transfer coefficient from the convections multiplied by the temperature difference. So we have the average temperature minus the convection temperature, the infinity or ambient temperature. Then we need to multiply it by the surface area of the fins. So fins dia ada two surfaces kan, permukaan atas, permukaan bawah. Permukaan sisi dia biasanya dia nipis je. So fin, let's say if dia macam plate lah, thin plate kan. So dia macam thin plate and then attached to the body. So this is the this is the main body tadi, which is where we have the very high temperature. So we attach the fin to this body. So when you are, let's say, to predict this heat dissipated from the fin element untuk satu single element, then you have to consider the surface tu. Kita ada surface atas ni dengan surface bawah ni. Okay, so we have two surfaces untuk satu fin. So this calculation untuk satu fin. Untuk satu fin. And then if we have an array of fin, to get the total heat dissipated or heat dissipation from the whole fin, then we multiply it by the number of fin itself lah. This is HE actually refer to one fin, and then kalau kita ada actually dia macam gini lah, kalau fin 1 kita ada 1 H1, kalau fin 2 kita tambah lagi, kalau ada 10 fin tambahlah, tambah sampai H10. So to simplify this equation, so dia ditulis macam gini lah. So this is the equation. Biasanya untuk design kita nak tahu single element tu berapa dia boleh kita boleh dapatkan the heat dissipation from a single fin. And then untuk satu-satu sistem elektronik yang kita nak pakai, biasanya tak cukup satu fin. So we have to put more fin. So from there you can, if you know one heat dissipation from one fin, then you will be easy for you to know how many fin is required to remove the heat from the main source tu tadi tu. So dia bukan macam simply saya nak pakai 5 je lah, saya nak pakai 100 fin lah. Kan boleh buat macam gitu, but it's not the best way lah. Tapi if you can calculate it accurately, then it's much more easier for you to determine how many fin is to be used. But kalau guna banyak sangat, then it will cost you the material kan, cost untuk material pun mahal, besi, aluminium you have to pay, you have to buy, bukan dapat saja kan. So you have to imagine what is the optimal number of fins to be used. Bagus juga tu buat soalan final tu, get the optimal number of fin. Alright, I think that's all untuk thin fin. We've done with the theoretical part, and then this is just an example. Let's look at the example. Alright, let's say we have a metallic fin. So diberi dia punya thickness 0.1 cm dan juga panjang dia adalah 10 cm dan width dia adalah 1 meter. So you have to be very careful lah dengan this term, the length, width. Length ni which is dalam arah sini length, width which is in that direction. So this is the width. So this is your base. Base ni dekat sini lah, base. Sini the base. Alright, so assuming this is the base, so you have discretized your element into several number of points. So then you can simplify it seperti dalam gambar ajar ni lah. So we are to solve this using 3 elements, and then this is the one that is exposed to the ambient. Maksudnya dekat sini we have Q4 lah kat sini, Q4. So it says that has a thermal conductivity K. So this is the material that we use lah untuk metallic fin. So this is the conductivity. It extends from a plain wall whose surface temperature is 235. So that means we know the T base T1 ataupun T base ni, which is given by 235. Then the convection heat transfer is given by 9 watt per area per degree Celsius with the T ambient which is 20 degrees Celsius. So you have H equal to 9, T equal to 20 degree Celsius. So the convections occur on both sides. Untuk fin memang dia akan berlaku on the both sides. So now let's look how can we deal with this. So when we discretize the element, then we have to prepare the K matrix as usual. Then you assemble it as usual as well. So yeah, this is that can go very detailed. So we have a similar process. And then you start calculating the elements H transverse matrix H by using the given equation. So kita ada H L bagi dengan 3 T, then we have a square matrix of 1 to 1. So substitute in these equations, then assemble, then you will get this the global metric for the heat transfer matrix. So in the process pun very straightforward. Then you prepare the R element heat rate vector, which is by using the supply equations. So apply to each of the local element, then assemble it as well. And then you rearrange the equation in the form of the system of linear equation K plus H and then multiply by T equal to R. So kamu akan dapat system of equations as shown in this slide lah. So sama juga dengan topik yang sebelum ni, you have to assemble the global system of linear equation terlebih dahulu sebelum kamu eliminate the row and columns sekiranya we have the boundary condition that allow us to do it lah. So in this case, we have the system of linear equations ready. Then we look at the boundary conditions. So we have the boundary condition, which is known boundary conditions at nodes number 1, which is the temperature is 235 degrees Celsius. So in that case, we can eliminate the whole row and column for all element K, H, T, and R. Then we will get something like this lah, as shown in this slide kat sini. To eliminate the whole row and columns. And then once we eliminate the system of linear equation according to the boundary conditions, then we have, as you can see here, initially kita ada sampai dekat sini je. Initially we have the equation sampai kat sini je before we eliminate it. So this is our K, this is our H, this is our T, this is our R kan. Okay, so once we eliminate the row and column, so as you can see here, we have to modify the right hand side equation to include this term here. So as you can see, this term is came from the K matrix. Then we multiply by T, and then we bring the matrix from the K matrix tadi tu. So kalau saya boleh go back dekat sini. So when we eliminate this, what we have to do, we bring all of this ni. We bring all of this to the right hand side equation. Yang ni pun we bring it to this side of the equation. Tapi as you can see, kita bukan bawa dia ke sana je, but we multiply those equation K and H tadi by the temperature, by the base temperature tadi tu. Alright. So when we bring it to the right hand side, so you have to be careful. We deduct it from the right hand side equation, bukan kita tambahkan dia. So this is how we deal or do the treatment according to the boundary conditions lah to our system of linear equation. So we remove the row and column, which is we know the temperature. Then we bring the elements yang apa tu from the K and H matrix to the right hand side. Tapi kita deduct it from the K and H, the component, and then we multiply it by T base. So kita ada T base kat sini, which is something like that lah. So this is the treatment due to the known boundary conditions. So when you have done this, actually you rearrange simplify this equation so that you can solve the system of linear equations to obtain for the unknown. So this is the unknown. If you solve the system of linear equations, so kamu boleh dapat benda ni, then you can plot lah from the 2, 3, 5, you have next node 211, 197, 19, 2. So this is node number 4, 3, 2, and node number 1. So this is your temperature. Alright, just a little bit more dekat sini. So when you have this, you should be allowed to compute the heat loss from each element. So untuk elemen 1, so this is element 1, you can actually determine how much the heat loss in element number 1, how much the heat loss in the element number 2, and in the element number 3 as well. So to get the total heat loss, so we just add lah untuk satu elemen heat loss for one element, which is the total adalah tambah lah H1 tambah H2 tambah H3. So ini adalah untuk heat loss untuk satu elemen. And then kita ada, okay, ni lah betul lah. This is the total heat loss. And then if you are to calculate the heat dissipation tadi tu, kan, then you have to consider the surface area and also the the temperature difference between the average and also the ambient temperature. So I think that's it for the whole of our course. I think this will be the last topic and we have finished it. All the topics in our course, which is finite elements method. So kita ada sikit masa lagi. If you think my lecture today is very fast, because I would like to finish it today. Topik dia pun very simple. So you can repeat the lectures by watching the recorded lecture that I post in my YouTube channel. So lah. I would like to take maybe we have around 3 minutes, and at the same time I would like to share the attendance as well lah, attendance. So I would like to highlight a bit about the test, your test and your final exam. So before this, when we have face-to-face lectures and meeting, we really limit our number of elements that you have to solve to maximum what we call it 3 element kan. So we limit kepada 3 elemen saja supaya kamu boleh solve pakai your calculator. But this time, since everybody at home, then in this test, test 2 and final exam, you may need to solve more than three unknowns. Um, so in that case, you actually can use any way to solve that particular system of linear equation saja. Actually, kita nak tengok the process from how you discretize the model, how you set up the equation up to system of the linear equation. You